This video is going to be going through the medium level questions on work, energy and power. Question 1, we are talking about an e-bike with an electric motor with a total mass of 95 kilograms moving up an incline. The cyclist begins at rest, so 0 meters per second, and accelerates uniformly in 21 seconds, and the distance is 110 meters. Calculate the kinetic energy of the e-bike and the rider at B. So because acceleration is constant, we can use a Suvat equation. I know we're not talking about gravity, which is when we usually use a Suvat equation, but as long as the acceleration is constant, they still apply. So the one that we're going to use is distance equals initial velocity plus the final velocity divided by 2 times t. So if we put in the numbers we know, the distance travelled is 110, initial velocity is 0, final velocity we do not know, dividing it by 2 and then timesing it by 21, which is the amount of time. If we rearrange that, we get the final velocity is equal to 10.5-ish. I've rounded that a little bit. And then with that final velocity, we can do our kinetic energy equation. Ke equals half mv squared. So I'll pop in half. The mass is 95. And that final velocity 10.5 squared, and the Ke is 5,213 joules, or 5,200 joules if we're going to two significant figures. Moving on to 1b. Calculate the gravitational potential energy gained by the e-bike and the rider between A and B. So we're going to use the gravitational potential energy equation, which is mg times the change in height. And to calculate the change in height, we are going to use trigonometry. So if you look at the diagram, we have the angle is 5. We know the distance along the hypotenuse, I'll label that h for our hypotenuse, is 110 meters. And we are trying to work out the opposite. So this is our adjacent, this is our opposite our angle. So we've got h and we want O, so we're going to use the formula triangle for sine. So we're going to do the sine of the angle 5 times our hypotenuse, 110, and that's going to give us a height of 9.6 meters. Then that number we can pop in our GPE equation. So we'll do the mass, 95, times gravity, 9.81, times 9.6. And we'll get an answer of 8935 joules. Question 1c. Between A and B, the work done by the electric motor is 8,100 joules and the work done by the cyclist pedalling is 11,900 joules. Calculate the wasted energy. So we're first going to work out the total work done, and that's going to be both of those added together, and that gives 20,000 joules. To work out the energy wasted, we are going to take the work done minus the GPE that we've worked out minus the kinetic energy that we've worked out. So we're going to do 20,000 take away 8935 take away 5213, and we will get 5852 joules. And for question 1d, state 2 causes of this wasted energy. So you could have said it comes from the air resistance or the drag, the friction between the tyres and the ground, or that the energy is transferred into heat or thermal energy. So for question 2a, we've got a pump storage system used to generate electricity, where water flows down the pipe and through a turbine. Show that the maximum possible speed of the water as it arrives at the turbine is about 50 meters per second. So for part A, we've got to think about, to get its speed, we're going to use the equation for kinetic energy. However, the kinetic energy the water is going to gain is going to come from the gravitational potential energy that it has at the top. So we're going to say the kinetic energy is equal to the potential energy. So that means our kinetic energy equation will equal our gravitational potential energy equation. So before we start putting any numbers in, because we're making these two equal to each other, we can cancel out the mass. There's no mass in the question, we don't need it. Then we can rearrange this. We've got half v squared is equal to g, and I'm going to change it from from delta h just to h. And then we can rearrange this just to get v. So we're going to have 2gh and then square root it. And then we can pop in the numbers that we've got. 9.81, and then the height that it's being dropped from is 120 meters, and that gives us a velocity of 48.5 meters per second. Part B, I think, is rather tricky. I'm going to move this up so we've got lots of space. The volume of water flowing into the pipe, into the turbine every second is 4.5 meters cubed. Estimate the radius of the intake pipe required for the system. So first thing we're going to do is we're going to presume that this is a cylindrical pipe, and then an equation that we should be able to work out, and I'll explain how in a second. The velocity is going to equal to the volume per second divided by the area. So this is why I think this is quite tricky. This is not an equation that is given to you at all, but we can look at our units to work out whether this makes sense. So volume per second is meters cubed per second, and then we'll divide it by meters squared, and what that would give us if we cancel that out is meters per second. So that sort of proves that this equation works to work out our velocity. So we're going to rearrange this then to work out our area, because that's where we're going to get our radius from in a minute. So area is going to be the volume per sec divided by our velocity. So the volume per second is 4.5 meters cubed, and the velocity we did work out above is around 48.5, and if we divide that we get an area of 0.0989 meters squared. The area of a circle is pi r squared. So if we arrange that for the radius, we'd have the area divided by pi square rooted. So if we pop in that area up there, 0.0989 divided by pi, all square rooted, you will get a radius of 0.17 meters. Question 2c, the water leaves the power plant chamber at a speed of 19 meters per second. Calculate the maximum possible power output, and we've also got the density of water given there as well. So to work out the power, that is the energy per second, and that's going to equal to the change in the kinetic energy, because it's going to slow down. That's where we get our power from. So to do our kinetic energy change, we've got half times m times v squared, but we've got a speed before and we've got a speed after. So we're going to do half times the mass, and I'll show us where we get the mass now. So our mass, we're going to use our density, and we're also going to use our volume. So if we take our volume from the previous question and times it by 1,000, we get 4,500 kilograms. So that's the mass that's passing through every single second. And then for our velocity change, we've got our initial velocity from part A, and we're going to take away the velocity in this question, pop that in brackets, and therefore our kinetic energy, or our power, is going to equal 4590000 watts, which is roughly 5 megawatts. Question 2D is asking about energy losses. Explain 2 possible reasons for this energy loss. And here's a selection of 4 that you might have put. It says heat or friction in the turbines, frictions at the walls of the pipe, turbulence within the pipes, or electrical heating in wires. Question 3A. A parcel of mass 23 kilograms drops from a delivery chute onto a conveyor belt as shown in figure 1. The belt is moving at a steady speed of 1.5 meters per second. The parcel lands on the moving belt with a negligible speed and starts to slip, it takes 0.75 seconds for the parcel to gain enough speed to stop slipping and move at the same speed as the conveyor belt. So part A, we are calculating the change in kinetic energy. Personally, I think there's a lot of words in this question that we don't really need. So ignore them and just think about what we know. So our kinetic energy is going to be half of the mass times the velocity squared. So the mass is 23 and the velocity is 1.5 meters per second. And we're going to square that. So our kinetic energy is 25.9 joules. So what happens in these first 0.75 seconds is it starts at 1.5 and it ends up at negligible speed. So we're going to say 0. So that means the change in velocity is the one that we're going to use for our V to work out our change in kinetic energy. Moving on to 3b. The average force acting within that time is 50 newtons. Calculate the distance between the parcel and the end of the delivery chute 0.75 seconds after the parcel lands on the conveyor belt. Assume it does not reach the end of the conveyor belt. So from our previous question, we've got the change in KE is equal to 25.9 joules. We are going to be using work done for this, which is going to be equal to our change in kinetic energy, and that's force times distance. We have the force, it's 50, so we can rearrange this to find the distance. So it's our work done divided by the force, sorry, and we are going to get number 0.5175 meters. Question 3c. At a later stage, the parcel is being raised by another conveyor belt as shown in figure 2. The conveyor belt is angled at 21 degrees to the horizontal and the parcel moves at a steady speed of 1.5 meters per second without slipping. Calculate the rate at which the work is done on the parcel. So when we're talking about work done, we are talking about energy per second. So we're going to sort of presume this is all happening within 1 second. So if we to think about the distance per second, first of all, and by the distance, I mean the distance upwards. So I'm going to draw the triangle that's going to help me work this out. 21 degrees. I want to work out the height because in a minute I'm going to use the GPE equation, gravitational potential energy. So we know it's going 1.5 meters per second in this direction. About how much is it going upwards? So if you have a look at this triangle, we are going to use sine. So to work out the distance per second, it's going to be 1.5 times sine 21, which gives you 0.5376-ish meters per second. So we are then going to use GPE, mg delta h. So the mass of the parcel from earlier in the question is 23, times gravity, times the height that it goes per second. I realise that it's a speed there rather than a height, but it is the distance per second. And we're going to end up with 121 watts. So watt is a joule per second. Question 3D. The efficiency is 66%. Calculate the power input. So just a reminder, efficiency, which is usually given to us in a percentage, is equal to the output, the useful output, divided by the total input times 100. So if we pop our numbers in there, 66% is equal to our output, which we just worked out, divided by our input times 100. So if we rearrange that, we get the input is equal to 121 times 100 divided by 66, and you will get about 183 watts. So that is our input power. Question 4a is about an electric wheelchair powered by a battery. There's a load of information there, but we don't need a lot of it for part A. So for part A, we're going to show that the average power output of the battery is about 200 watts. So we're going to use an equation, which I'm not sure if we just certainly haven't used it yet in Unit 1. I'm not really sure where it comes up. But the electrical energy is equal to the potential difference, or our voltage, times the charge. So we've got our voltage, our potential difference, EMF. We use lots of different terms for it, not really sure why. But we've got 12 volts, and we're going to times it by the charge, 9.8 times 10 to the 4. And that's going to give us our electrical energy of 1.176 times 10 to the 6 joules. So quite a lot of energy because of that times 10 to the 6. We are then going to work out our distance we're going to work out our time from this speed and this distance here. So we can use speed equals distance over time. So we're going to rearrange that because the one that we are missing is the time. So distance divided by speed. So the distance travelled is 15 kilometres, which is 15,000 metres, divided by the maximum speed, and that's going to give us a time of 6,000 seconds. And then we are going to use power is equal to our energy divided by our time. So our energy given by our battery over how long it can run for. So you're going to pop in this number divided by 6,000 and you're going to get 196 watts, which is very close to the 200 watts from the question. Question 4b. During the journey, forces due to friction air resistance acts on the wheelchair and its user. Assume all the energy is used to move the wheelchair. Calculate the mean resistive force. We are going to use the equation power is equal to force times velocity. So any of the power we're providing forward is basically fighting against that resistive force going backwards. And we're going to rearrange it to work out what that force is. So that's going to be our power divided by our velocity. So the power we just worked out in our last question, 196 watts, and we're dividing by the velocity. Also, we used it in our last question, 2.5 meters per second, and we are going to get 98.4 newtons. So in question 4c, the wheelchair is now going up a hill at an angle of 6.5 to the horizontal. Calculate the maximum speed when the power output is 200 watts. You can assume the resistive forces due to friction are the same as in part B. So that means we're going to be using our answer from part B from before. First thing we are going to do is work out the total mass, which you need to read the first bit of the question, but we're going to take the mass of the person plus the mass of the wheelchair. So in total, we're going to be 100 kilograms. That is because we need to work out how much force is working on this person due to gravity now they're going uphill. So if I model them as a block, the force going down is mg and our angle is 6.5. We need to know how big this force is due to the force due to gravity, but parallel to the slope. So that force is going to equal the weight, mg, but we're also going to take the sine of the angle. So that's going to be 100, the mass, times 9.81, gravity, times sine 6.5. And that force is going to be equal to roughly 111 newtons. So we've got that force working down, but we've also got, so we've got the total force going on them. So we've got that force, but we also have the one that we worked out in the question before, and that is going to be, I'm going to add it, 78.1.4. So that is the total force acting down on it that needs to be overcome. So that's 189.4 newtons. And then we're going to use a very similar equation to the one above, basically the same equation. Velocity, or the speed, is equal to the power divided by the force. So we're going to take our power, 196. I know it says to use 200, but actually we worked out earlier that it was 196, not 200. You could put 200 in as well. And we're going to divide by the force, which is 189.4. And our answer is equal to roughly 1 meter per second. So that is the speed of our wheelchair. For question 4D, explain how and why the maximum range of the wheelchair on level ground is affected by the mass and the speed at which the wheelchair travels. So when you're talking about the mass, if we increase the mass, we're going to reduce the range of motion. It increases the friction on bearings or tyres. More energy or power is used to accelerate to get to the top speed. And the user in the wheelchair have a higher kinetic energy needed to move. And if we increase the speed, we're going to reduce the range, and also air resistance increases with speed. On to our final question, 5. So question 5a, we've got a roller coaster car. This is its top speed. There's lots of information here. We don't need it all for the first one. We've got a total mass, we've got a force provided, we've got an angle, and we've got a distance for that angle. So for part A, to calculate the work done, we're going to use the equation for work done, force times distance times cos of the angle. So we're going to take the force, 5,500, times it by the distance 1.5, and times it by cos 28. When we do that, we will get the work done as 7284 joules, which is roughly, to two significant figures, 7,300 joules. 5b, calculate the maximum height that would be reached by the car if all of the kinetic energy went to gravitational potential energy. So its kinetic energy is going to be equal to half of mv squared. So half times the mass, which was in the question as 7,900, times the top speed velocity, because we're going for its maximum height, so we're going to take its top speed velocity, and that gives us a kinetic energy of 1.42 times 10 to the power of 7 joules. And then we're going to pop that in our gravitational potential energy equation, and that's going to be equal also to our GPE, which is mgh, and we're trying to work out h. So to get that, we're going to take that 1.42 times 10 to the 7, and we are going to divide it by our mass and by our gravity, and from that you will get a height of 183.49 metres, or roughly 180 metres. For question 5c, explain why it does not reach the maximum height that we've calculated. So that's for 2 marks. So we've got to say that there's going to be work done against the friction, drag, air resistance, any resistive forces that are working against motion. So that's our first mark. And the second mark, what happens when we do that work done is that our kinetic or gravitational energy is transferred into thermal energy or heat energy, which is basically wasted in this system. On to our final question, final part of the question as well. Question 5d, the car reaches point C, which is at a height of 155 metres above A. Calculate the speed the car would reach when it descends from rest at C to its original height at D if 85% of its energy at C is converted into kinetic energy. So we're going to start with its GPE at C, which is mg change in height. So the mass is 7,900, times it by gravity, times it by our height, and we get 120.12345 joules. So that's our GPE at C. And then we want to work out our kinetic energy at D, which it says in the question is 85% of that number that we've just worked out. So we're just going to take that number and we're going to times it by 0.85. And we should get 10,210,493 joules. And then with this, we're going to pop that number into our kinetic energy equation, half mv squared. So to rearrange to find our velocity, what we're actually going to be doing is the square root of 2 times our ke from there, divided by our mass, 7,900. And what we will get when we type all of that in is 50.842 metres per second.